literally, I can't even say, a leading particle physicist joining us to do an artful piece entitled Neutrino Monologues. Please welcome to the City Code stage warmly, Dr. Deborah Harris from Fermi Lab.
Thank you. Wait a minute. Oh, great. Okay, well, thank you very much. So first of all, I'm a little curious. How many of you have ever heard of neutrinos? Please raise your hands. Oh, excellent. Well, maybe. Okay, fantastic. How many of you have heard of neutrinos before the Nobel Prize in Physics announcement this week? Still same number. Good. Okay, well, I think they're really interesting. They're one of the most abundant particles in the universe. There are more neutrinos than there are protons and neutrons by a factor of 700 million. But they are much, much smaller than protons and neutrons. We can't see them, just like you can't see protons and neutrons. And they weigh over 1 billion times less. Without neutrinos, the sun wouldn't shine. The world wouldn't be filled with elements any heavier than hydrogen. So imagine how boring that would be. And they were created at the time of the birth of the universe. They've been around ever since, and they've been in every corner of the universe ever since. On the other hand, they are the hardest particles to see because they almost never interact. They are everywhere, but they're never part of our everyday lives. Because of the simple fact that they are almost impossible to see, neutrinos have had a long and very amusing history. I'm here to tell you that history, but I want to do this through the voices of people who you don't usually hear talking about science. So I am not an actor, I don't play one on TV, but I'm going to try and become each of those other people to tell you the story. So the neutrino first made its appearance in a letter written by it's a famous letter actually. It's written by a very famous physicist, Wolfgang Pauli, and the first monologue is spoken by the unknown person who is assigned to read that letter. Zurich, December 4th, 1930. Dear radioactive ladies and gentlemen, can you believe this? Energy is missing from the atom. We don't understand it, so naturally, my supervisor, Wolfgang Pauli, writes a letter with some outlandish idea to explain it, and then he sends me to read the letter at this conference. As the bearer of these lines, to whom I graciously ask you to listen, will explain in more detail, blah, 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 I have hit upon a desperate remedy to save the law of conservation of energy. Mr. Chadwick over in England, you see, he's examining radioactive decays where these beta particles are made, and he observed that there was less energy at the end than there was at the beginning. So Professor Pauli's guess is that there must be some other particle that is leaving this radioactive decay, but it's escaping the detector without detection. So because it leaves no trace in the detector, he reasons that it must be neutral, electrically neutral, and does not interact too often. But really, if the professor actually believed in this theory, do you think he would have just sent one of his minions to read it at a conference? Surely he just doesn't want to face up to Niels Bohr. Dr. Bohr claims that this can all be explained by Heisenberg's uncertainty principle. He says that in quantum mechanical processes, energy is just not conserved. Professor Pauli's excuse for not being here does not inspire confidence. Unfortunately, I cannot appear in Tübingen personally, since I am indispensable in Zurich because of a ball on the night of the 6th and 7th of December. I've seen the professor dance. He is hardly indispensable. But you mark my words. If all of this is bunk, the humble messenger will bear the brunt. On the other hand, if this new particle turns out actually to exist, then Professor Pauli will become even more famous than he already is, and 100 years from now, nobody will even remember the messenger's name. So sure enough, nobody actually knows who read that letter. After Pauli, through his student, made this bold prediction, his colleagues were skeptical. Luckily, Enrico Fermi, who I have to say, Fermi Lab was named after Enrico Fermi, in case you're wondering where that name came from. Enrico Fermi was not so skeptical, and he worked out a theory that described the laws that would govern these neutrinos. The only problem is that he couldn't get his theory published. So the next story is told, and this is true, really. The next story is told by the editor of Nature magazine. 1934, London, England. Dear Dr. Fermi, thank you for the submission of your manuscript, Tentative Theory of Beta Rays. we regret to inform you that we cannot publish this in our journal because it contains speculations too remote from reality to be of interest to the reader. Sincerely, Sir Richard Gregory, editor of Nature magazine. No use mincing words here. I understand Enrico Fermi is a brilliant man, but this time he has gone too far. This theory he proposes that beta decays take place because a neutron can change into a proton, emit a beta particle, and this thing he calls a neutrino is simply of no use. I will grant you that the theory he describes in this manuscript does describe the pattern of energies of the beta particles that come out of these radioactive decays. But Dr. Fermi has had plenty of time to see those results, so I would hardly call that a prediction. And I will grant this too, that I am intrigued by the symmetry he proposes. Just like a neutron is a proton, but with its charge removed, so the neutrino would be like an electron, but with its charge removed also. Then Dr. Fermi goes on to calculate what would happen if the radioactive decay goes backwards in time. In that case, a neutrino would come in and strike a neutron, and then it would produce a proton and an electron. And here is when any intelligent reader would find something else to read. According to Dr. Fermi's calculations, the neutrino is over 1 million times less likely to react than a proton. How on earth are we going to get 1 million neutrinos or millions of neutrinos to test this idea? I tell you, Dr. Fermi has some cheek. He wants Nature, the world's premier scientific journal, no less, to publish a theory about a particle that, on the off chance it does exist, cannot even be measured. I say let him publish his musings in some other journal. He must have a cousin or something who could arrange for that in Italy. So sure enough, those of you who can read Italian know, this Fermi's theory on beta radiation was published in Italian and also German before it was eventually published in Nature magazine. So I have to say, the next monologue in this series is the one monologue that is based on pure rumor and not on facts or interviews. Some of the principals have even denied that there's any truth to this story, but the rumor's too good for me to leave it out. So the character in this case is the divorce lawyer for Leon Lederman's first wife, Florence Gordon. Leon has done many wonderful things in his long and fruitful career, both in and out of the laboratory, and I only hope that he will forgive me for giving voice to this rumor if, in fact, he ever does find out, and I will leave it to you to not tell him. New York City, 1974. As they say in this business, if you've seen one divorce, you've seen one divorce. I've represented women who were divorcing their physicist husbands many times, but I don't think I ever learned as much physics for a case as I've learned for this one. Before I started representing Florence Gordon in her case against Leon Lederman, I didn't even know what the word neutrino meant. But now I can tell you quite a few things about them, and one of the things I've learned is that it takes a long time, usually decades, to make progress on neutrinos. Just take their discovery. They were predicted to exist way back in 1930, but a neutrino wasn't actually seen until 26 years later at a nuclear reactor. At least Pauli was still alive when the neutrinos were discovered. He died just 2 years later. So what does this have to do with my client? Well, my client's husband developed a completely new way to study neutrinos. Instead of just putting some detector next to a reactor to study them, my client's husband used a particle accelerator to make a beam of these particles. He was trying to see if the neutrinos made by an accelerator are the same kind as the ones that come from reactors. When reactors make neutrinos, they produce electrons at the same time. But when an accelerator makes neutrinos, it produces muons at the same time. I learned that the only difference between a muon and an electron is how much they each weigh. These physicists, though, they think that neutrinos don't weigh anything. So the neutrinos that get made with electrons should be the same as the neutrinos that get made with muons. But my client's husband proved that this is wrong after seeing the signal that those neutrinos made from the accelerator made in his detector. I think this is huge. Instead of having to study neutrinos using the reactors, now scientists can just build a beam of neutrinos of whatever energy they want. But I'll bet you that, as usual, it will take a long time before anyone realizes how important this is. So this is why I have to make sure my client's interests are served. Here she's been married to him for 20 years, raised their 3 children, and in that time, Leon Lederman has gone from a starving graduate student to a full professor at Columbia. But she has the bad timing to get divorced now, and I bet it'll take years before the rest of the world, including the Nobel Prize Committee, realizes how important this discovery is. I am going to make sure that if someday Leon Lederman does win a Nobel Prize for this work, Florence Gordon will get half of it. So as you can tell from the picture, Leon Lederman did, in fact, win a Nobel Prize for that work many years after his divorce. The next monologue is told by a miner I interviewed who met physicist Ray Davis and John McCall, shown here, while working in the Homestake Gold Mine, which has been in operation for 150 years. This mine, you'll see, features prominently in the history of neutrinos, both last century and this one. Leeds, South Dakota, 1985. I've taken the elevator down the mine with Mr. Ray Davis for over 20 years, and I have to say that I really feel sorry for the man. I know it's tough being a miner. I should know. I've been a miner for well over 20 years, but I would have never guessed that it's just as tough being a chemist. If you had asked me before I met Mr. Davis, I would have said those guys, they're all too busy doing stuff you and I will never understand. But you know, when you work in a mine, everybody takes the same elevator. So when they started doing this physics experiment underground, I started riding the elevators with these physicists. These guys are a chatty group, I can tell you. Anyway, after enough years of rides, I think I figured out a thing or two. But I was telling you how hard it is to be a chemist. Can you imagine a job where you have to build a swimming pool-sized tank deep underground, fill it with bleach, and then wait for these weird particles for the sun, which he calls neutrinos, to interact? When one of those neutrinos interacts, it's supposed to change a proton into a neutron. But when that proton is inside a chlorine atom in that bleach, it turns that chlorine atom into an argon atom. And the only way Mr. Davis knows this is that he has to wait long enough, and then he has to drain the literally handful of argon atoms out of this chlorine-filled swimming pool. I would call him a magician, not a chemist. Anyway, so this poor Davis fellow designs this amazingly challenging experiment. He sees a bunch of argon atoms, proves once and for all that yes, the sun does shine thanks to nuclear energy, since, he tells me if it didn't, there would be no neutrinos to change the chlorine into the argon in the first place. Before now, every time people tried to figure out what made the sun shine, they ended up with a prediction that it should have only lasted a few thousand or a few 100,000 years. But apparently it's been around much longer. Even Darwin had that figured out. It's just that nobody knew how. But Mr. Davis's neutrino solved the problem. So you think everybody would celebrate, right? Break out the champagne? But no, no champagne for Mr. Davis. Instead of calling this a great success because Mr. Davis proved once and for all that the sun does send trillions of neutrinos to the Earth every second, everyone is pointing fingers because the number of neutrinos he measured in that swimming pool was 3 times too small. At least, that's what his buddy, Mr. Bacall, tells me. I've seen how careful Mr. Davis is. He can't be wrong, let alone by a factor of 3. It's Mr. Bacall who must have gotten it wrong. I've tried to cheer Mr. Davis up. I told him, hey, Mr. Davis, those neutrinos probably didn't get to the detector because it's been so darn cloudy these days. He keeps laughing at that one for some reason. Apparently, neutrinos pass easily through clouds, or Earth for that matter, which is why the detector is so deep underground. The ground keeps all the other particles from turning chlorine into argon. Maybe Mr. Davis should just go into something easy instead, like politics. Sure enough, Ray Davis and John Bacall were both right, and that was discovered by one of the gentlemen who won the Nobel Prize in physics this week. An experiment up in Canada, headed by Art MacDonald, was able to make 2 separate measurements with the same exact detector. One of those measurements was the number of electron neutrinos, which is what Ray Davis's experiment was able to measure. But the other measurement was the total number of neutrinos, which is what John Bacall's theory predicted. So they were both right, actually, which was good, because they actually were good friends in real life. And so each one couldn't really point the finger at the other one. So this next monologue is inspired by the other experiment that was honored by this week's Nobel Prize. So the Nobel Prize has this interesting requirement that you have to actually be alive to win it. So while this week's winner from Japan is alive and well, Takaki Kajita, who's shown here, and he's actually the person who got to announce this big breakthrough that the experiment made in 1998. There's another man, Yoji Totsuka, shown here, who many thought would win for his leadership on the same experiment, Super Kamiokande. But sadly, he died of cancer at the age of 66, 7 years ago. This next story is told from the point of view of Totsuka-san's doctor. July 2008, Kashiwa, Japan. Usually, physicists make the worst patients. They think, first of all, medicine is easier than physics. Then they think doctors don't understand anything about statistics. And then, on top of it, they want you to explain how all of their equipment works. But I'm really going to miss Totsuka-san. The first time I met him was right after he was diagnosed with cancer. At that time, he was the director general of the biggest laboratory of Japan. This is a man who could accomplish whatever he set out to do, and he had a real passion for these particles he calls neutrinos. I know now that I put neutrino sources into my patients' bodies for diagnostics, but those neutrinos travel through those bodies without leaving a trace. Totsuka-san told me that neutrinos are also made when high-energy protons hit the atmosphere and create other particles that decay while they're traveling towards the Earth. In fact, physicists know that there are 3 different kinds of neutrinos, and 2 of those kinds are made in the atmosphere. The physicists also know that those neutrinos should be produced at the same rate all over the entire planet. Can you imagine if a source of food or fresh water was created equally all over the globe? What a different world that would be. Anyway, if you could build a detector that could see these neutrinos and measure the direction that they were coming from, you know that the ones that are coming from the top of the detector must have been created in the atmosphere just above where your detector was. On the other hand, if you see neutrinos coming from the bottom of your detector, you know those were produced in the atmosphere that was a whole Earth's diameter away. And if you're really, really clever, you can build a detector that not only measures neutrinos from all different angles, but can tell which flavor of neutrino they are, whether or not they're the kind made by reactors or the kind that are made by accelerators, because both are produced in the atmosphere. So how did Totsuka-san get to be director general of the biggest laboratory in Japan? He built a detector deep under a mountain, as big as this 20-story hospital building, and he filled it with 50,000 tons of water. Then he led an experiment that measured the directions of these neutrinos for each of the 2 different kinds that were produced. 10 years ago this month, that experiment showed that while the electron-flavored neutrinos did seem to be coming equally from all over the Earth, the other flavor did not. The ones coming from the other side of the planet were missing. Totsuka-san told me that being able to compare the different kinds of neutrinos from all directions was really what convinced the world that neutrinos do weigh something, and that opened up a whole new field in particle physics. Not only did he do that, he did it twice. When there was an accident 7 years ago that destroyed over 1/3 of this giant detector, the very next day, Totsuka-san announced to the entire world that it would be rebuilt, and sure enough, within a year, it was done. And this is the worst part about my job. I was told by many people that if Totsuka-san could have lived just another 18 months, then he was likely to be awarded the Nobel Prize. So here I am, unable to change the course that cancer took in one man's body, while Totsuka-san changed the direction of an entire field. This last monologue is about a new experiment that is being planned that will take place both at Fermi Lab, 30 miles west of here, and in that same Homestay gold mine in South Dakota. Fermi Lab has been improving on Leon Lederman's original neutrino beam design and is currently home to 2 neutrino beams. One of those beams shoots neutrinos actually all the way up to northern Minnesota to 2 different neutrino detectors way up there, 450 miles away. Those neutrinos just go through the Earth, and physicists are measuring the neutrino interactions way up in northern Minnesota. But Fermilab is working on a more powerful beam that will go an even longer distance to make better measurements more precise measurements on these particles. So this story is told from the point of view of a mother from South Dakota whose daughter is studying to become a physicist. October 2015, Leeds, South Dakota. When my daughter and I first received this invitation to see an underground laboratory, I was against it. Why should we take a tour in the same gold mine that has killed so many men in my family? I know, I keep hearing it. Mining has gotten a lot safer now than it used to be. But I've always had mixed feelings about the place. My family's been working in the mine for over 100 years. In fact, my grandpa was one of the miners who excavated the cavern for that first experiment. I figured that when my daughter won that Davis-Bacall scholarship to go to college, we were done trying to earn our living underground. Why go back now? Of course, I don't know how many of you know my daughter, but my daughter was dying to go on this tour, and I cannot win an argument with her. So we both went on that tour to see what has been done to the mine after the miners left and the scientists took over. Because of this scholarship, my daughter may even work there this summer, believe it or not. It's crazy. I never thought I would see my own child working in a physics lab, but she's practically there. What's next, the White House? After going on this tour, I see that these physicists are not all like those guys on Big Bang Theory, although clearly some of them are. They especially like to talk in that long elevator ride down to where the experiments take place. Just like those guys on TV think that their work is so sacred, these physicists view this mine as sacred too, not just because of what they're doing, but because of its history. In fact, being deep underground makes their experiments possible in the first place. Would you believe that while we protested the working conditions down in the mine, the physicists protested when the folks were threatening to shut down the mine? I'm not sure I buy any of this, but these physicists say they will do experiments in the mine to tell them if their theory of how the universe came to be is correct. They say that in the very beginning, there were equal amounts of matter and this stuff they call antimatter, something that can collide with matter and create pure energy. Yet, all they see today is matter. They make this antimatter stuff in their laboratories, but they can never find enough of it to tell the difference between, between the way matter and antimatter behave to figure out what caused this big imbalance, because all the antimatter that was there in the beginning of the universe isn't here anymore. They say that neutrinos may provide the answer. If they can see that neutrinos produce more matter than antimatter when they interact in a detector. And how will they discover this? You are not going to believe this. They're going to make a beam of these particles 800 miles away, all the way over in Illinois, and then send them here to South Dakota. They want to measure how those neutrinos change over time and to see if there's an matter-antimatter difference that develops over time. And all of this could tell them if their picture of how the universe came to be is correct. I don't know. Given these crazy stories I've heard about neutrinos, I would say you can't predict anything about what they will do next. What I do know, though, is that thanks to the generation of miners who lived and died here, we might find out that neutrinos are the reason we are still here. And my daughter's getting a college education. I don't know what she'll discover with it, but I am sure her kids will know a lot more than we know today. Thank you.
Thank you, Dr. Harris. So I don't want you to leave without letting folks ask you some questions about neutrinos. Right?
Since you already have heard of neutrinos, I'm a little bit wondering what you're going to ask.
Any questions for Dr. Harris? Right here.
So you said that neutrinos can be created in either spin-off an electron or a muon.
Correct.
Is there anything different about the neutrinos themselves that come out of these interactions, or is it the particles that they interact with beforehand?
So the thing that Leon Lederman discovered, so the way you can tell if a neutrino was created at the same time as an electron or a muon is how that neutrino then interacts when you're in your detector. So if the neutrino stays exactly the same between when it's created and when it's produced, then it would make the same kind of particle at the end as it was created with in the beginning. So it seems crazy to think that these particles that don't weigh anything know what particle they were created with at the beginning, but that's what Leon Letterman's experiment showed, that the neutrinos created with muons create muons when they interact, and the ones that were created with electrons create electrons when they interact in a detector. So that's if neutrinos always stay the same. What we know now is that they don't stay the same because of these two experiments that just won the prize. But it's because of the way they interact in the detector. That's what tells you what flavor of neutrino it is.
Hi, thank you so much. It was very creative and interesting. I really enjoyed it.
You're welcome.
So since you've demonstrated so much creativity, I wanted to give you a creativity challenge. A lot of us have active imaginations. I can't be the only one. And when you were talking about the beam of neutrinos that could go straight through the Earth, I was like, wow, that sounds like a really cool weapon for an adventure. But you also said that they don't interact very much.
Correct.
So the creativity challenge is if I wanted to write a, at least, respectably plausible adventure movie in which the world was saved by a beam of neutrinos, what potential threats to the world could I defeat with the beam of neutrinos?
Wow.
That question deserves a round of applause.
Yeah, that's good. So I guess the first thing is that I'm thrilled that, that you want to figure out a practical application for a beam of neutrinos. And I'm also thrilled that you want something to be scientifically accurate. So there was a movie called 2012. I don't know how many of you saw it. But in that movie, a neutrino beam was going to destroy the Earth. And the reason it did it is because, according to the plot, the neutrinos were going to interact not in the Earth, but only in the core, and then boil up the core of the Earth, and that would destroy the Earth. So that's impossible. They don't interact more in the core than they do in the rest of the Earth. It just couldn't happen. So anyway, so one thing that people have written about is using neutrino beams to communicate with faraway cultures. So we could not maybe destroy anybody, but we could at least send them signals very, very, very slowly. But we should work together and figure something out.
One more question.
Thanks. So is there anything that neutrinos do react with? So for example, could they be somehow involved in dark matter?
A lot of people thought that perhaps they could be the answer, the solution to dark matter, but there are not enough neutrinos in the universe to make the dark matter, to make as much dark matter as we see evidence for. But there's some parts of, some people think that some kinds of dark matter could be some kinds of neutrinos, but not any of the three I talked about here.
I lied. More questions.
I was just wondering about the accident that happened at the super...
Oh, the Super Kamiokande mine, yeah. It was
a quarter
amazing.
of it got destroyed?
So what happened is that, so this is a picture of the mine. It's like I said, it's 50 meters tall. It's like 20 meters wide. And they have to drain, so these two people are actually on a boat, and they're polishing these glass covers of these phototubes. So there are something like 11,000 phototubes, which is basically something that gives off a signal, and it's like this wide around, okay? And what happened was they were doing some maintenance, and so they have to drain the whole tank and fill it back up again. And while they were filling it back up, there was some phototube at the bottom of the tank that imploded. And then that set off a chain reaction. And that broke every single phototube that was below the level of the water. So it was literally a third of the detector went boom, and it was just horrific. But they really did rebuild it in a year and take data. And they're still taking data now.
Anyone else?
So I got a question over here, back here.
Oh, hi.
So I don't know anything about like the new model of physics. I knew protons, neutrons, the atom, electrons, that kind of stuff. What is the relationship between neutrinos and like the Higgs boson, or what is the boson? Well,
So the Higgs boson is completely a different particle. The Higgs boson is something that people, well, first of all, it's a particle, but it's also, people think about the way that people are trying to understand how particles get mass in the first place, why they, different particles weigh different amounts. And they think that it has to do with the interaction with something called a Higgs field. And neutrinos, because they weigh so little, but they weigh something. We know that they don't weigh zero, but they weigh something. So they must interact in some way with the Higgs boson, but very, very little, much, much less than all the other particles. But it is funny because for the longest time, I mean, certainly the textbooks that when I was in college, the textbooks all said that neutrinos don't weigh anything. And I remember somebody once came up to me after a talk and they said, but wait a minute, my textbook says neutrinos don't weigh anything, but you're telling me they do, but they really do. So neutrinos are really separate, though, from the Higgs boson. And yeah, so.
Dr. Harris, thank you so much for joining us.
Thank you for asking me. It was a pleasure.